So what I thought we could do today is actually talk a little bit about the what people refer to as like the wave equation, like the classical wave equation, like the one that you would study first in like course on partial differential equations. Because so the idea is that we kind of already did most of what I wanted to tell you about classical mechanics. And then the idea is like in quantum mechanics, like the analog of Newton's equation or like the Hamilton's equations is called Schrodinger's equation. But that is some sort of like wave equation. That's also how it's called. So for it to make more sense, we kind of have to have like a little bit of an idea of what wave equations are. And so what are some of the mathematical properties? So I'll do kind of like a little bit it will feel a little bit more like a bunch of like mini topics today because I'll just tell you kind of like a few things that are kind of good to know when thinking about like a wave equation and also like infinite dimensional vector spaces, which you also need to have like an idea of what's going on there. So, and once we do that, then like, yeah, we can go back a little bit more to talk to the physics part, but it is beneficial to just have this as like an aside or like some sort of like background so that like then it does make more sense like when I tell you what happens again when you kind of like study quantum mechanics. So like for the wave equation, the idea again of the most like basic form of the wave equation is, well, you have like some sort of string, and you like move the string around. So like there will be some waves propagating along the string. So like maybe if it's like, yeah, like maybe that represents the string. And so like you know, the function that appears in the wave equation is kind of like the function that gives you the height of the string with respect to the x-axis. So let's say you have like the x-axis here. So originally, maybe you think of the string being along the x-axis, and then you move the string, and then you have some waves propagating. And so u of xt, then the name for the height at a point x. So if here's x, that this height, you could call it y of xt, but I'll call it u of xt. So okay, so yeah, and like as time goes by, like like if you think about it, like kind of like giving like pulse to the string, then you would imagine like what you would think happens is kind of like the wave propagates along the string. So over time, you maybe like the height here decreases and things like that. So like it does make sense for like the height to be a function of position and of time. Okay, so. The wave equation is an equation that this function is supposed to satisfy. So let's see, I think this, I always forget where I should put the V. Okay, let's see. Yeah, this is okay. Right, so like the function dependent on two variables and the wave equation is just an equation that relates like the second partial derivatives of this function. Well, like the kind of like the pure partial derivative, like the one with respect to x and the one with respect to t. So there's like no mixed partial derivatives in this equation. Um, okay, and then here b is a constant. So here b is a constant. Um, which sometimes I'll keep track of and other times I won't. But if you're into this type of analysis, like the way you should think about it, if you have, if you think about it in terms of partial derivatives, if u represents like the height, right? So that would be measured in units of length. So here this has units of length, and when you take second derivatives with respect to time, you get on the left-hand side length over time squared. So uh, the left-hand side has units of length over time squared. And then the right-hand side, if you ignore the v, right? So the right-hand side has units equal, well, to the units of v squared, right? And then this one has units of length, and then when you take a second derivative with respect to x, like that would put 2 units of length in the denominator, so like you cancel one of the units of length, so you get units of 1 over length times 1 over length. Okay, and because like, physically both sides should have the same units, so, that tells you that the units of b are length over time, and so that is, so in some way, it will correspond to some sort of velocity, and it's kind of like the velocity that the wave would have, like in more or less. So, again, like not that I will always keep track of this constant, but like, it's kind of useful to like, if you want to have like a more like concrete physical interpretation, to think of this constant and stuff like, I mean, for us mathematically, it's just a constant, right? But if you were to give units to everything, then yeah, it would be kind of like something that has like the units of velocity, so that, or speed, because we're in one dimension. So something that has like units of speed, so that like both sides make sense. And that is really, again, like I'll tell you if I have enough time today, like kind of how you would try to solve this equation. So you would see that literally you get something that has velocity, like propagates kind of like at this velocity or something of that sort. Okay. Is that making sense so far so good? So that's kind of like how the wave equation looks like. Again, like the most basic baby version of the wave equation. There are a bunch of generalizations, but this is kind of like enough to see like some of the things that happen here. So like, so you're like in general, when you try to solve an equation of this, like, well, at least to try to find solutions to this equation, it does make sense to assume that the function you're looking for can be differentiated. Otherwise, this wouldn't even make sense. So like at a minimum, you would need like like the second partial derivatives to make sense. Like you don't lose, like you don't wait, like, there's not too much of like a loss in generality to just try to find solutions that are like you would call smooth. So for now, like as a first approximation, we're going to try to find like all the functions that are smooth. So like in the sense that it has like, you can take as many partial derivatives as you want. And that satisfy the wave equation. So let's call that, so we're seeking solutions or smooth. And so you could start just by defining a set, you could take a set, like you could call like a set, make a set out of all the solutions to this equation, right? So you would say like, let's call it V sub wave. I'll call this, I mean, just to emphasize that it's like, um, as, um, is related to the wave equation. So the set is just consists of all functions. Okay, so this depends if like the function u depends on x and t. You could think about this as functions from R2 to R, which are smooth, right? Smooth and satisfy the wave equation. So that satisfy. I'll switch to this other notation for the partial derivative just for now, because it just takes less time to write it down. So, you consider like, think about trying to find all possible solutions and make that into a set, right? So the set just like has all the solutions thrown in. And then, you know, the first thing that you would notice, like, if you ever do this like in differential equations, even maybe like there's a little bit of this is discussing ordinary differential equations, is that this like equation is linear, right? Meaning that if you have two solutions, right? So like the first like really important observation um, is that the wave equation is linear, meaning that if you want and you two are two functions that solve the wave equation, or let's just say that belongs to this set, right? Because that's the whole point of having defined this set. So if you have two solutions to the wave equation, then any linear combination of these two continue to solve the wave equation, just because like the partial derivatives are linear, right? So by linearity kind of or let's just say belong. Um, here C1, C2 are like arbitrary constants. That making sense? So one second. It is not the empty set, right? Why is that not the empty set? Because like the zero function belongs here, right? Like the zero function is there, and literally that corresponds physically to you have like the string along the x-axis and you do nothing to it, right? You just leave it alone. So you don't perturb this, like the wire or the string. So this set is non-empty, right? So it does contain the zero vector, like the zero function or zero vector, and so um it's non-empty since you know since like u of x comma t equal identically zero, right? Like zero for all values of x and t does solve the wave equation. So I mean, it is a non-empty set, and it has like this linearity property. So that essentially tells it's enough to just say that like this will be a vector space, right? Like it's essentially so this one forms a vector space of the wave is a vector space. Over the real numbers, at least for now, because I'm just working it. Like, I mean, I'm working right now with like coefficients, which are like real. Or, so it's a vector space, So the first thing that once you know that it's a vector space, like, something that you learn in linear algebra to ask is what's its dimension, right? Like, or what's a basis, right? Like those are like natural questions. So like the next step, and that's related to also finding solutions which are different from the zero vector, right? Because as of now, it could be that the only solution to this equation is a zero solution, which would be like a very like silly equation to work with. Obviously, it won't be the case that's like that is not what's going to happen, right? But so like the two main questions are like which are kind of related. Are what's the dimension, right? So what is the dimension of this vector space over the real numbers, right? And can you find like useful basis, for example? Can you find Okay, and then, so what's going to happen, and I will start explaining this today, it's like, well, what will happen is that the dimension of this vector space is infinite dimension. Okay, so this, like, what will happen is that, so like, just like some preliminary answers, it's like the dimension of this vector space is like infinite, right? Okay, and then once you know, I mean, and there like that just means like literally not finite, right? Like so that means like that for any n you can find n+1 linearly independent vectors, like right? That like that's one way to think about just like an infinite dimensional vector space. And then the other question is that once you have a infinite dimensional vector space, like what do you mean by a basis of that, right? So like, I mean, it is possible some of you have seen this or not, so I'll just kind of start from scratch because I don't want to assume necessarily that you have done this before. So like, what, like, there is like a notion of basis for a vector space, which I'll tell you about in a bit, which is more useful, but for that you need like a dot product or an inner product, and that takes you to what's called like a Hilbert space. So, and so the basis, like, you have to kind of like build like something that you would call a basis that's just like more like suited for like the fact that this is infinite dimension. So the basis will be related to this notion of Hilbert space. Which is this idea of like a Hilbert space. I mean, people just call them Hilbert spaces. Like no one calls them Hilbert vector spaces. I'll just put the vector here in parentheses. But that is really like the core of like, the formalism of quantum mechanics. Like, like the Hilbert space is kind of like the main like actor in like the Hilbert space and the wave equation, like the Schrodinger equation, are kind of like the two basic ingredients of any quantum mechanical system. So like it's kind of like good to have like an familiarity with that before like I write down for you like maybe 1 week or two like the Schrodinger equation. Okay, so like as I said, today's kind of a bunch of mini topics. So like the first thing is just to tell you, okay, there's this wave equation. The vector space is going to be infinite dimensional. So let me now just tell you a bunch of like just give you some examples of infinite dimensional vector spaces, just to have like an idea of like how things change a little bit like versus like the more like familiar case of that finite dimensional vector spaces. So let's talk about this. Okay. So let's start just first with something that's actually finite dimensional. Okay, but and then I'll just increase its size until I make it infinite dimensional. So this is like the following is probably an example you would have seen like in linear algebra. Um, let's just define something like this. This is going to be the polynomials. So I'm going to define this as a polynomials of degree less or equal to n. So like the elements of this set are just polynomials that you could write something like this. Of degree less or equal to n. So here, so AI, here's like just any constant, right? AI are arbitrary numbers. So just to make this a little bit more concrete, like, if you have something like p less or equal to two, or by that I just mean like the polynomials of degree less or equal to two. So like I just mean some things that literally you can write as a naught plus a1x plus a2x squared, right? Where um or a naught, a1, a2 are like real numbers. Okay, so that's just that. And like if you add polynomials of degree less or equal to two, you get a polynomial of degree less or equal to two, right? And if you multiply a polynomial of degree less or equal to two, you times a number, you also get a polynomial of degree less or equal to two, right? So that's just to say that these like something like either of these two cases, like it's like just a specific case, either of these two are vector spaces, like like so. For any n, forms is a vector space, right? Does that make sense? And here you probably know the dimension. Like this one is actually of finite dimension, right? So what's the dimension of this vector space? Yeah.
N plus one.
Right, right. It's just n plus one because, like, yeah, for example, so yeah, it's n. So for again, so the dimension of p less or equal to n is n plus one. For example, the dimension of p less or equal to two would be three, right? And why is that? Because if you look at the specification here, to specify a polynomial of degree two, you need three arbitrary numbers, right? Like the stuff with the x is kind of like fixed in the formula, right? So the thing that you're really allowed to change in this formula are like a naught, a1, a2. So one way to think about like one way to see that this is of dimension three, that really you can find like an isomorphism, linear transformation between this and R3, right? So like there's like an isomorphism T from to R3, which just takes like a polynomial, right? A naught x, a naught like a1x plus a2x squared, and just sends it to, like the coefficients, right? Like the constants in front of the powers of x. Right, and that is a bijection, a linear transformation, invertible, blah 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 blah. So like like it will establishes like the dimension is three, and so in acts like also by automatically from this it follows like a basis for this space, right? And so a basis would be like this has like dimension three, so like the basis is like 1 0 0 0 1 0 and 0 0 1, and that corresponds to like the like the polynomial degree zero, the monomial x, and the monomial x squared, right? These like are like the three vectors that make up the basis, right? So far so good. Okay, and then kind of like what's nice about working with the of course, like this is just like R3. But one of the nice ways of one of the things that are nice of like thinking about it this way is that then you can define like linear transformations, which kind of make more sense on this side than on this side. So for example, one thing that you can do, like, so here's like, and this will be a good example because it's actually really useful for what we'll do next. So here, like, you can do, like, you can think of the derivative as a linear transformation here, right? Because the derivative, this sub x, I'll just put the x here to emphasize that it's going to be differentiation with respect to the x variable. I mean, in fact, it kind of lands inside P of n minus one, but that's fine. So like, you can, if you have a polynomial of degree up to n, and you differentiate it, right? Um, Right, if you differentiate it, you just get, I mean, the derivative lowers the degree of the polynomial, but then that continues to have degree less or equal to n, right? So, like, yeah, like in something like, in something like, it's kind of useful to always do it like for a specific example, like, this one. So if you do it for like the polynomials of degree, 2 or less, and you get it a1 plus 2a2, right? And then if you use like the isomorphism with R3, right, this is just like a particular linear transformation. Like it's just taking a0, a1, a2 into, now this goes to degree 0, right? So, and then this goes like, sorry, right? Then this, now that like is in the middle, and there's nothing in degree 2, so it just goes like this, right? And there's like the matrix that does that, right? So now you can forget like the fact that this came from polynomials, right? Like you just have like a transformation on R3 that does this, right? So you can find like a matrix for the derivative, right? Oh, this is like so what? It's going to be actually upper triangular, has zeros on along the diagonal. It's actually very simple. Right? So that is going to be the matrix that represents like the derivative on the space of polynomials, right? Matrix. Is that okay? Is it making sense? And then, okay, what is something that's useful about doing things this way? Because then, yeah, there are questions that you wouldn't necessarily have asked about it, like if you just think about it like as a derivative of polynomials. So once you have like the matrix, you can be, okay, the fact that it, like, it does depend a little bit on the, there's certain things that are specific to the choice of basis, right? Like, so the way that we are choosing the isomorphism with R3 does give you this particular representation for the derivative. But there are things that are independent of the basis, right? So for example, the spectrum, like the eigenvalues are independent of the basis, right? So so for example, you could ask, well, what are the eigenvalues of, so the other word for eigenvalues, yeah, it's like the spectrum. If you have, I don't know if you have seen that other terminology, but actually this name comes from quantum mechanics, for example, for like the eigenvalues. I'll tell you more about that later. Well, it comes from chemistry, I guess. But the eigenvalues here, I mean, it's upper triangular, right? So the only eigenvalue is, like when it's an upper triangular matrix or lower triangular matrix, the diagonals are the eigenvalues. And that's like an invariant statement that doesn't depend on the choice of basis. So like the eigenvalues are just zero, right? Like what that's just saying is just zero. Because it's upper triangular and it has zero along diagonal. Okay. Which makes kind of sense because like other, there's the only way to like, if you think about it kind of like as an eigenvalue, eigenvector equation, right? You're trying to find like a polynomial whose there, like after you apply the derivative is lambda times a polynomial, right? Like that's kind of like the eigenvector equation for like for the derivative. And yeah, like the derivative decreases the degree. So the only way for this to kind of hold is if like lambda is zero, right? Like and the so okay, so that is so then and yeah, like then you could ask like what's the dimension of the kernel, right? Like so the kernel in this case, what is it? So the kernel. Well, like, this will work, I mean, here that you can also use it from the fact that it's upper triangular, but it's just should be one because any constant polynomial has derivative zero, right? So, just like the space of constant polynomials. Is that okay? Is that making sense? Okay, so like this is okay. Like the next step, after you do this, like for like a finite n, is yeah, just to um, just to let n be infinity, right? So you would define like P of infinity. I mean, I guess, I don't know, probably I'm not saying this is kind of like standard notation. But like you would just take this to be the space of all power series, like formal power, what you would call formal power series, like, formal in the sense that I don't care anything whatsoever about convergence. So I'm not making any claims about convergence. Like it is really like just like an expression in terms of x, right? You let it like this be like a formal power series. So let me just put here formal to emphasize that, right? Formal power series. So you're in here, like you're just really ignoring analysis at this point, right? Like it's no convergence, no questions about that. So ignore analysis for now. So like that allows you to just like let like the AIs be arbitrary numbers. Otherwise, you would have to have requirements, right, for the series to converge. So like here, like AI is like just like whatever it wants to be in R, right? And it's kind of okay. It's kind of reasonable or easy to see that like each P of n, right, is a subspace of P infinity, right? Any polynomial of degree less or equal to n is naturally like a form of power series. You just like take the remaining terms constants to all be zero, right? So like as a subspace, right? But we already knew that the dimension of this was n plus one, right? So because it's like a subspace, like this is telling you that the dimension of the formal power series has to be infinite, right? Which is like, does that make sense? In fact, this like, is in correspondence if you just follow the, P infinity, right, is like isomorphic to what you might want to call R infinity, right? Like, so instead of like saying like R2, R3, R4, right, like it's R infinity, which just is just like literally the space of like, infinite vectors, right? So A naught, A1, A2, A3, blah, 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 but it continues forever, right? And this, like, it is just like sequences, right? Like this is just like literally like another way to list a sequence. So this is just like this, the space of infinite power series is the same as the space of like sequences, right? Like, and this makes sense because when you have sequences, you can add them in real analysis, you can multiply a sequence by a number, so like this is also in correspondence to what you would call like real value sequences, right? Meaning, and what are real value sequences? There are functions from the natural numbers into R, right? So there's another way of thinking about these things, right? So, because this would be like, right, well, I guess for sequences, sometimes you use like this notation or also like X sub n, right? So this is kind of like, f of zero, this is f of one, right? F of two, right? So a sequence is just like dealing a list of an infinite list of numbers, right? And since they're all the sequences, that yeah, like you don't have any conditions of like whether the sequence converges or not. And so there are no, again, there in this setup, there are no questions about convergence, right? And so far so good. So like it's kind of like cute to see all the like these isomorphisms explicitly. And then like just by analogy, you can still just like take a formal derivative, you know, of like an infinite power series by differentiating them term by term, right? I mean, you apply the same definition as before. Again, as a formal power series. And you know, if you thought about this as like a matrix representation, right? You would say, okay, then, you know, before it was like upper triangular matrix, right? For the derivative, it is kind of like the same as like continues to be like upper triangular. I mean, here like you have to be like a bit more careful, but you know, like the matrix for like I'm writing kind of like this is what like how the derivative matrix looked like for polynomials of degree less or equal to 2, right? So what would happen like afterwards, like you know, is that you know it just continues like you know the like the diagonal amount above the main diagonal is like 1, 2, 3, 4, 5, 6, blah 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 blah, and then there's zeros everywhere else, right? So like bunch of zeros here, bunch of zeros here, and like just to emphasize this, like this is kind of like the main what you would like kind of call like the main diagonal, right? And so like the line among the diagonal, well, if that makes sense, like above the main diagonal is where like the coefficients appear, right? Everything else is zero in this matrix. And so like this is like the sense that, you know, in which you can think of, for example, something like a derivative as an infinite matrix, right? Like with certain isomorphisms put in place. So then that's like actually like like more like an early approach to quantum mechanics, which kind of Heisenberg found, which is one where they refer to as matrix mechanics. So matrix mechanics is kind of like where you have the derivatives and other things like represented as infinite matrices. Um, and he kind of like found the rules for matrix multiplication and other things like from like some like very natural assumptions. Okay, but now, so what's like, what is the point of doing all this? That it also tells you, you know, that you do have to be careful. So everything like it's kind of like working right now by analogy, but there are things that can fail miserably if you just like go by analogy, right? Like so here's like where you do have to be a bit more careful. So you know, if you thought about this as like an infinite matrix, then you could ask, oh, okay, what are the eigenvalues, right? Like so here's like where like the analogy fails, right? So here's where analogy fails. Right, so you could ask what are the eigenvalues of the matrix, right? Right? So if you just play by analogy, you say, well, this is still kind of like upper triangular. Maybe zero is the only eigenvalue, right? Like you could say, well, okay, zero. So zero because it's upper triangular. And that would be kind of incorrect in this case, right? So this is not the right answer to have. So this one would be wrong. Because like as you already know, I mean, this is like the point of the exponential, right? If you think of the exponential as like as a form of power, well, it does converge. But if you thought about it just like as a form of power series, you know, well, let me put like should have been I. So okay, yeah, should have. You know, if you think of exponential as a form of power series, then precisely the derivative will return the exponential, right? Like, so. So like in whatever like natural definition, like you would like to say that eigenvalue one, think that it one is like an eigenvalue of the derivative, right? that is like a natural requirement. So that just mean, what that means is that you have to be more careful when you try to find like the eigenvalues of like a matrix when you're like in the infinite dimensional setup, you know? Like it cannot, you know, if you just like go by analogy, like, you know, in like, oh, it's something like upper triangular or something of that sort, then you do have you know, you do have problems. Like one of the reasons, like you can see why you could have more issues, like, you know, it's like, if you remember like like the order, like if you remember like that, so this would be like eigenvalue 1, right? If you remember like the original definition of the eigenvalue eigenvector equation, like in linear algebra, to find the eigenvalues, you rewrite that as saying that the determinant of A minus lambda identity equals 0, right? But then it does boil down to like, you know, where you have the issues, like there is like, okay, what's the determinant of like an infinite matrix, right? And then you do have to, there is impossible to avoid questions of convergence. I mean, you cannot just like remain kind of like in the formal setting where you just like play without ignoring the analysis. When they say infinite dimensional, you do have to at some point consider analysis, because then you would have to ask things like what's the determinant of a matrix. In fact, like you could ask like what's the, even like something like what's the trace of a matrix, right? And or like upper, like infinite dimensional matrix, that's what I mean. And for that, like that does not always exist, and the ones for which that exists are called like trace class matrices, where you can actually take the trace and things of that sort. So like, you know, everything kind of has to become more careful, just because like, you know, yeah, you can, like there are many things that do work more or less the same as infinite dimensions, but other things do break down very quickly if you just like ignore any issues like coming from the fact that you have like infinite dimensions. Okay, so this is just like, for now, like the important thing is like, yeah, like sometimes it is useful to think about the derivatives and other things as infinite dimensional matrices. But if you want to find something like the eigenvalues or things like that, of the matrices, then yeah, you have to not like, you have to think a bit more about what you mean. Okay, so that was the first minute topic for today. So far, so good. Any questions about this? Okay, so the second mini topic is like, we do want to have like a better sense of like the concept of a basis. So there is like a definition of basis that you can do. You can give infinite dimensional vector spaces, which is kind of like the same as you know, as a one infinite finite dimensions, where like, you know, a vector, you know, you have like a collection of vectors is like a basis if every vector like is a finite linear combination of a subset of that collection. You do need something called like Zorn's lemma or the axiom of choice to show that every vector space has a basis, like in, so like it does require like a powerful theorem. But I will take a slightly different approach, because when you, in this context, when you talk about quantum mechanics and more like analysis, when you like like the concept of basis you care about is like the one that comes from a Hilbert space. So like, let's just talk about that for now, because that's like the real the interesting concept that we want. Okay, so just before like, so to talk like about the basis properly, we do have to think a bit more about like convergence and things like of that sort. Now we do have to say a little bit more of analysis. So now it's unavoidable. So if you think about like, so it's kind of like the problem with all analysis is always infinity, right? Like that's where like the the fear. So like, how do you control infinity? So in like, if you look at something like this, right? There are two sources of infinity, right? Like for a space like this. Two. So the first one is that if you like that, literally it is a series, right? It's a formal power series, so it's like an infinite sum. So the first source is like that you're dealing with an infinite sum, right? Like you have a series. So, but the other one that is a little bit more hidden in this representation is that if you actually want to think about this, like, you know, in terms of convergence and other things, like, so you want to think of X as a variable that takes value somewhere. You know, if you have, the way I'm writing it up is to suggest that X is kind of like a can take any value on the real line, right? So if you think about X as like not like a formal variable, but like an actual variable that can take different values, if X is allowed to take different values, which is kind of like what that function notation suggests, right? Um, then, like, you know, like typically the way you think of X is like as an arbitrary number on the line. So X takes values on like an infinite like set, right? In as of now. So then for now, then it would be taking values on the, say, on the interval negative infinity to infinity, which is infinite itself, right? Like like the real line is an infinite set, right? Like in the sense of like having like infinite length, for example. Say, for example, infinite length, not like cardinality. Or measure if you prefer. So, you know, it is useful when you're trying to make this work to, you know, just work, handle, kind of like they have you have these two sources of infinity, right? And just like you want to just a priori like just work with one of these two problems at once. So the easiest thing to do is kind of like just to fix this problem of X taking infinite values, right? By, for example, by kind of moving away a little bit from this representation and working with a different space, which is like the space of periodic functions. Okay, so that will actually, you know, kind of help us take control of this situation. So, like, what I'll do is kind of like, you know, so what I'm going to change a little bit the setup so that we can just focus on the fact that we could have like a series in general. So for that, I'll just modify to a little bit, get rid of two of the issue two by working with you know a periodic variable. So like really we're going to work on, you know, if it's like a periodic variable, like you can think about it being on the circle, but I'll just think about it on the line, but like everything repeats itself, say after period 2 pi. So by working with a periodic variable. Okay, so like for example, I'm going to be you know, let's just call this V for vector, like again for vector space. Now I'm going to look at the functions U. Well, let's call them okay, let's call them F for now, just to not be too biased. So I'm going to look at real value functions, you know, but they're going to have all period to pi. So period to pi. So for example, like, you know, I'll think about it this way. I kind of want, you know, like usually when you have a function of period to pi, you can think of it as being defined on 0 to pi of the interval 0 to pi. I'll just think about it as being defined on the interval, you know, minus pi. So that's, this is what I mean first. But so I'll think about them as functions. So I'll think of them as functions from So I will just think about them as functions defined on negative pi, on the interval negative pi pi, and the periodicity will be imposed by asking like the values at negative pi to agree with pi, with. Right, so like, kind of, you can go back and forth between both ways of thinking about it, right? And I'll ask just to make again, like our life easier for now, I'll just assume that the functions are smooth, meaning like you have all the infinite derivatives, so. And they're continuous, blah, 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 blah. More, it's like a bit of an overkill, you don't really need that, but it's kind of like nice to do it that way. And then, okay, let's see, so. And then what happens here, like, is that, you can, once you have like a space, like, again, like this is still like a vector space, like, so this is like the way I want to think about this for now, but, so B is going to be a vector space. And because sum of periodic functions is of period to pi is periodic of period to pi, rescaling a periodic function of period to pi is periodic of period to pi, etc., etc. And by the same lot, like, and it's still, we'll see like in a bit, like it's still like infinite dimensional. So like it will be infinite dimensional, which is infinite dimensional. Okay, so now the way I'm going to start, the way that's kind of more useful to think about these things, for what we'll do in a couple of classes is that you do want to have some sort of like dot inner product on this space. Okay, so there is like a natural dot product, inner product you can define here. So there's like inner product. Which is like, if you have two periodic functions, f and g, everyone has seen this notation for the inner product, right? I mean, so if you have two periodic functions f of g, what you can do, like, is integrate them, right? And then, if you, of course, like you cannot just integrate arbitrary periodic functions, like they could have like bad behaviors, but like, if you ask everything, I mean, once everything is continuous, like that's more than enough on a bounded interval to integrate them, for example. So that's one of the advantages of working with things being periodic, that you don't have to worry about like having proper integrals, because otherwise like the integral will be over R, and then you have to throw in more like assumptions to make the integrals finite, right? And then, yeah, you can check, for example, that, this is a dot inner product, right? Because like, what are the conditions, like that f, right? Like that is just like the integral, like f squared, which is not negative, right? And it's also easy to check that it's bilinear, right? Like linear in each entry, because like the integral is like, um, is, linear, and it's non-degenerate, right? Because if f is 0, right, like the only way for like the square of means that, yeah, and because again we're assuming, I mean, I imagine like, you have had like probably already this, say, courses in real analysis where you have like these silly functions where like they're zero everywhere except at one point, and then at one point maybe they're like, or like these functions which are zero at the rationals and one at the irrationals and things like that. Of course, like then those are more confusing, but then they are not continuous, right? Like they wouldn't be smooth. They're kind of like outside like what we're looking at for now. So yeah, if like the fact that they're just continuous, like if the square of a continuous function integrates to zero, like then yeah, like the function itself had to vanish like altogether, right? So far, so good. Questions about this? Okay, so you have a vector space with an inner product, right? So okay, so here, so before telling, like I'm almost done for today, but before telling you what like, so this is already enough to, just having this like will be enough to show that this is infinite dimensional, because like it is easy to find orthogonal vectors or orthogonal functions inside this vector space. So what is the quintessential example of a continuous function like sine and cosine, right? So for example, if you define like here, like n for n an integer, right? Like let's say an integer. And we have like a sine of or cosine, like this could be sine of 2x, cosine of 3x, whatever. They are all I mean, they will be they have periods less than 2 pi, but like in particular, they do repeat their values after 2 pi. Like by period, I don't mean the smallest number. I just mean that after 2 pi, you return to your value. So like something like sine of 2x has period pi, but in particular, it repeats itself after 2 pi, so like it's still like they're all elements of this vector space, elements of B, right? And then and it is easy to check that they are orthogonal. If you do the dot product between any two of them, in fact, it doesn't like, you could do like the dot product between two different values here, like so. I don't know, about here, assuming that n and m are different integers, right? Have you done this calculation before? Like, it is just because there's this a bunch of identities for the product of sines. The product of two sines is kind of like a sum of cosines or something like that. Like, or like, how is it like, I mean, if you go to Wikipedia and look like for list of trigonometric identities, you can say another way to check this is that, you rewrite sine and cosine into, or you rewrite a sign in terms of like the complex exponential, and that's easier to like check that this does give zero, since like the product of sines is like yeah, it's like a sum of cosines or sines. Its product of sines is a sum, and they are going to, once you evaluate them and integrate them, like they will vanish at the endpoint, so you get something that gives you zero. It's not like, again, it's not like a bad, like, it's not like a super difficult integration to check. But the same logic, like they kind of like integrate to, like when n and m are different, like they do integrate to zero. And also if you take like a sine and a cosine, that also does integrate to zero. So I'm just saying that all these sines, cosines are orthogonal, like, with respect to this inner product. And if you remember from linear algebra, when you have like a set of vectors which are perpendicular, they're automatically linearly independent, right? So since there's no restriction here, like how large the integer, like the n or m can be, all these collections are like, you have like an infinite collection of linearly independent vectors. So in the vector space itself must be linearly independent. So you have a infinite collection. So the dimension of B must be infinite. That making sense so far? Some good questions about this. Um, so, okay, now there are two things yet to say. So this is like, because we're wrapping this up. Okay, as I said, today's kind of like a bunch of mini topics. So this is cute. You have a vector space with a dot product, with an inner product, right, which is infinite dimensional. So this is really good. There's only one technical issue with this vector space. So you have, so what we have found so far, V is infinite dimensional, right? A vector space with a dot product, with an inner product, right? With an So the only issue with this thing so far is very like analysis centered. So the only problem is that V is not complete. Okay, so V is not a complete vector. It's not complete. Um, Meaning that not every Cauchy sequence converges. Okay, so once you have like a dot product, you can define a norm, right? You probably have seen this, right? Like you can take the norm of like you can take the norm of a function to be the square root of the dot product of the function with itself, right? And then you can define the distance between two functions to be the norm of f minus g, right? Sorry, again, since I'm not quite sure like how much you have seen this, like that's why I kind of like giving you all these definitions. So maybe it's a bit repetitive for some of you, but you know, so I'm just saying like once you have a vector space with an inner product, you have like a distance. Once you have a distance, that you can talk about like sequences of vectors or sequences of functions in this case, and then you can ask, is every Cauchy sequence convergent, which is like the main important thing of analysis, right? That's what makes art. That's why you cannot do analysis of on the rational numbers, or analysis over the rationals is way different from the analysis over the reals, because the real numbers are complete, right? And if you have seen like these constructions of the reals from the rationals, like exactly the point of the reals is that you kind of throw in all the possible Cauchy sequences, limits, and that's how you get the reals. Like, so there's this very elegant construction of the reals out of the rational numbers just by completing the space of the rationals, right? So there is like a kind of like in the same way in which the real, like, you know, the reals can appear as a completion of the rationals, you can kind of complete this vector space, right? Like I won't go into the details because that does require a lot of like measure theory. Like, so you can complete the vector space, complete it. So I should put here like what this means. No, so not every Cauchy sequence converges. Converges here. But there's a completion possible, so you can complete this. So there, it can be completed. It can be completed. And the cool thing is that it can be completed into, like, the completion will continue to be an infinite dimensional vector space with an inner product. And that's what people refer to as a Hilbert space. So Hilbert space is just like a vector space with a dot inner product that's complete, basically. So into a vector space V with an inner product. And that is what a Hilbert space is. And when people talk about a Hilbert space, is just that. So a Hilbert space is just a vector space. It's a vector space with plus a dot product or like an inner product, right? Um, plus like the completeness under, like, you know, the distance function from coming from plus complete. So again, like not you, like, I won't get into too many nuisances of what's going on out here, but the point is, like, this is almost like a perfect, like this example is almost perfect, except for the fact that, yeah, like not you can take sequences of functions here that do not converge and you want, which are Cauchy, so you do want to have like a limit for those. Okay, so that is one of the things that happen here. And so in quantum mechanics, like usually you do work on a Hilbert space. So that just means like working on a kind of almost what we have here. But yeah, when like this condition being satisfied. So for like, you know, because we're not doing like a big course on functional analysis, which is what this is really called to, like, you know, I will mostly be referring to this thing, but it's kind of useful to keep in mind. And yeah, like there are some arguments that are kind of like, will be kind of sketchy the way I say them because they're probably better phrased in like, you know, in the completed version of this. And so for example, just to maybe finish today with this, like what I'll tell you, what I'll start next time is telling you what's like the transpose of a transformation here, like the adjoint. That's like a very cool thing. But just to finish like today with like a little bit of the basics, once you have like a vector space, you know, with the dot product and this notion of convergence coming from the norm, then like the suitable notion of a basis, like, you know, so a basis for B, like in the sense of a Hilbert space, so a basis for B, or let's call it like a Hilbert space basis. Oh, or for V star, let's say, V completion. E is just like a sequence of vectors. It's a collection of, oh, it's going to be an infinite collection. An infinite collection. Of vectors. And the idea is that every vector here is a linear combination of the base. It's like kind of like how you would like, such that any other vector B is a linear combination. But in the sense of but in this like where CI is like a real number. So it's like, what I'm saying is that now this is like an infinite linear combination. So it's like a genuine series, but now this is fine because this is like an actual series. So here like, you do want like the convergence of this. Like, so by this, I just mean in the sense that the limit, right? Like the limit of the partial sums of this, what is a series? Like a limit of partial sums, right? The limit as, well, I should have put, I'll put I here, sorry. The limit of the partial sums, you know, as n goes to infinity, gives you back the v. And that can be defined because now you do have like a notion of distance, right? So it means that for every epsilon, blah, 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 blah. Like you have like the same notion of limit. So I'm just saying like, the point of having like a dot product, like an inner product is that then you can have a norm. Once you have a norm, you can have a distance, then you can talk about convergence of sequences. So this is actually like a statement that you can ask whether or not it holds. So like a Hilbert space is something where it's like a genuine like infinite sum with convergence included. So and the main theorem, like for example, in Fourier analysis, if you have seen this, is that these sines like cosines are like a basis for like the periodic functions, right? So like the point of Fourier series, right, is that, and I'll finish just with this. So the point of Fourier series is that like these like functions, sine and cosines are form a basis, right? For like the space of periodic functions, form a Hilbert space basis. So that means like that, you know, every periodic function can be written as a series of sines and cosines, basically. Form a basis for the space of periodic for B. Okay, so So yeah, like that kind of ties very nice. Like, having this language of like Hilbert spaces is like a very convenient way of like just like extending linear. This is like the best extension of linear algebra of finite dimensions to infinite dimensions that you can do once you have like the Hilbert space structure, because then everything it just kind of genuinely allows you to work with series with the notion of convergence. Okay, so next time what I'll do is tell you a little bit of how you can solve the wave equation, and also I'll talk about a little bit about the transpose of an operator, because that's an actual concept, very important concept, because what's the point of like having like a transpose, like, again, like when you have like a matrix, if you take its transpose, once you have a transpose of a matrix, you can ask for whether the matrix equals its transpose, right, which is symmetric. And that's, again, one of the best matrices that you could ever be. So you want like a linear for operators like differentiation, you want like to take the transpose of a differentiation, which is called the adjoint in general. And then you can ask for whether or not like an operator equals its transpose. And then that would be symmetric, and that would be then there's like a spectral theorem just in finite dimensions. So it's kind of also like what allows like the quantum mechanics setup to work well with like symmetric operators. Basically, we'll need as well. Okay, but yes, I'll tell you more about that next time. So I'll probably take another class to just do more crash course on infinite dimensions, like random topics, before like just returning to like the quantum mechanics thing. But it's kind of like good to have this like before like mixing it with the quantum mechanics, because then it becomes like a mess in your brains, like what's quantum and what's not. Like you can like definitely do this like just for classic, like classical mechanics, things like that. It has something to this. None of this has to do with quantum mechanics per se. Okay, so questions, yeah.
So when we're defining like a basis for a Hilbert space, are we requiring that it's accountable?
Oh, so that's a great question, which I threw under the rug. So for us, all the physical examples is that basis will be countable, but there are like these things called rigged Hilbert spaces. Where the space where the basis is not countable, but like say has a cardinality of the real number, so it's like the continuum. So yeah, so it is like for basically 99% of the applications, like the Hilbert spaces, always like you just assume that they have like a countable basis. But yeah, there are like sometimes extensions that are useful where like you do allow continuous um um continuous basis. But yeah, like basically, and there's kind of like a theorem, like like there's this theorem, like maybe I should try to mention it next time more precisely. But in finite dimensions, there's like this theorem that all finite dimensional vector spaces are like of the same dimension are isomorphic, right? So there's kind of like an analog of this for Hilbert spaces that like if say you have two Hilbert spaces with like with the countable basis, like then they're kind of like equivalent, unitarily equivalent. This is kind of like the von Neumann theorem. I think that's one of the things that we proved. But yeah, I'll probably try to say something about that. But in practice, we will kind of work with the very concrete representation for all this. So we don't care too much whether there's one or many Hilbert spaces. But yeah, there's kind of also like an isomorphism that for like the countable case, there's really, you can all kind of, because the thing is like if you have a Hilbert space with a countable basis and you have a Hilbert space with another countable basis, you just create like a map that says like, the first, like then you can list the vectors, right? So you just create like a map that says like the first basis vector to the first basis vector, blah, 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 blah. And then you just extend that by linearity. And yeah, basically that's kind of how it works. I think it's kind of persuadable. But yeah, no, that's a good point. There is like, you can just think about this countable for our purposes, but yeah, there's like way to extend this. But good. Okay, so let's end here. And next time I'll tell you more like details about all this stuff.